In the previous models, we had been looking at how the presence of errors in variables or the presence of proxy variables causes the estimators to become inconsistent. We saw that even dropping the proxy variables cannot remove this inconsistency. There is a bias that is going to be involved always, and so we need to find certain techniques by which we can avoid this problem. One of the techniques, the standard techniques that is used, is the maximum likelihood method, and we have seen how the maximum likelihood method helps us to estimate the parameters. But then when we do the maximum likelihood method, we need to put in certain restrictions, because there are too many parameters compared to the number of equations that we get. What we will discuss today is a different technique referred to as the instrumental variable technique, where we need not make such assumptions, where we only need to make a good choice of an instrumental variable, and we will see how we can do that in the case of errors in variable models. Before we look at the specific problem of the instrumental variable technique as applied to errors in variables models, let us look at what the instrumental variable method is. We have the usual regression model y is equal to x beta plus u. So, we have n observations. So, y is a n dimensional vector. There are p explanatory variables, and hence x is n by p. There are of course p corresponding parameters, and beta is p by 1, and you have the error, which is again n by 1. And if we use the ordinary least squares, then we have x prime y is equal to x prime x beta, and the least square estimator comes out as beta hat is equal to x prime x inverse x prime y. And as you know that beta hat, if we just substitute y here, then beta hat becomes beta plus x prime x inverse x prime u. Now, if x is non-stochastic, or if it is independent of u, even if it is stochastic, it should be independent of u, then obviously the second term on taking expectation becomes 0, because if you take expectation, if x is non-stochastic, the expectation goes right through and expectation of u is 0, and even if it is stochastic and independent of u, then we have these two components and expectation of u again is 0. Therefore, expectation of beta hat will be equal to beta. More generally, if you look at the condition that 1 by n x prime u tends in probability to 0, that is what happens if you have x and u uncorrelated to each other, then beta hat would, if for large samples, be tending to beta, because the second term would go to sigma inverse xxx, that is the variance of x or the dispersion matrix of x, into 0, because x prime u divided by n would be going to 0, and therefore, it would be tending to beta. Problem is, if x and u are correlated, then 1 by n x prime u will not be going to 0 in probability. It will be going to a constant, whatever its expectation is going to be like. And then beta hat will not be tending to beta, but will be tending to beta plus this constant sigma inverse xx into a constant, which is not going to go to 0, and we will have an inconsistent estimator. So, forget about unbiasedness, even for large samples this is not going to be consistent. And this problem that x and u are correlated occurs quite often in econometrics, in other fields as well. This happens when you have lag variable model, that is y is lagged with itself and with lags of x as well. When we have errors in variables model, as we have seen here, so in errors in variables we have the same problem, x and u are getting correlated. This happens for simultaneous equations models, where you are looking at a number of equations together, where there are a lot of response variables, not a single response variable. Now, so this is a very common phenomenon that we have. So, what do you do in this case? One method that we do is the instrumental variable technique, and in that we search for a matrix Z of the same order as x. that is, it is a p variable matrix. There are p variables, and of course, the n observations should give us z is equal to, z has dimension n by p, and z should be such that 1 by n z prime x should be going to some constant sigma zx, that it should be highly related to x. So, it should resemble x as closely as possible, and more importantly 1 by n z prime u should be going to 0 in probability. So, it should be uncorrelated to u and should be as closely related to x as possible. So, if we do that, then let us go back and look at the normal equations. How do you get the normal equations? We have y is equal to x beta, that is the model, plus u. Pre-multiply the whole thing instead of x by z. So, we have z prime y is equal to z prime x beta plus z prime u. And if you divide 2 out by n, the last term would be 1 by n z prime u, which would be going to 0. So, if we ignore the last term, then we come back to the and cancel out the n from the remaining two terms, we have z prime y is equal to z prime x beta. So, you have a new set of normal equations now. Instead of x prime y, you have z prime y. Instead of x prime x beta on the right hand side, you have z prime x beta. And your instrumental variable estimator for beta would be z prime x inverse z prime y. And if you want to check whether this is consistent, you replace your y by x beta plus u, and then the first term actually gives you beta, and the second term would be 1 by n z prime x inverse 1 by n z prime u. Of course, we can insert the n because we have an inverse in the first and just n in 1 by n in the second. So, that would cancel off this 1 by n. And by our conditions, 1 by n z prime x would be tending to sigma zx inverse in this case, but 1 by n z prime u would be going to 0. So, the whole of the second term would be going to 0, and hence beta hat I v, that is the instrumental variable estimator, would tend in probability to the parameter beta. So, what we have here is a consistent estimator. How do you get the consistent estimator? You use the instrumental variable z instead of x. Mind you, you do not change x in the model, that is a very common mistake that students make. You only use this partly to pre-multiply the model. So, if you look at the equation, you still have z prime x on the right hand side, z prime x inverse into z prime y. So, the x is not completely replaced, because if you do that, you are changing the whole model. And then this z also must be uncorrelated to u, so that when you actually do the asymptotics, this part would be going to 0, the bias part would be going to 0, and you get an consistent estimator for the parameter beta. Now, let us go back and look at our problem. Go back to the two variable model that we were looking at. We have the model yi is equal to beta naught plus beta 1 xi plus epsilon I, where yi is made up of yi star, which is the true value, plus some error vi, that is the contamination. Xi again is contaminated, and it is made of the true value xi star plus wi, which is the contamination in this case, and epsilon is the resultant of the errors. It consists of the model error ui, it consists of the vi, that is the error from the response, elements were 1, and the second column were the x's, x1, x2, xn, the n observations of x. Now, z would have the first column similar to x, because that does not create a problem. So, the first column of z should also be 1, whereas in the second column the xi's are replaced by either 1 or minus 1, as the case may be, depending on whether the xi is greater or less than the median. So, we have the z value now. Hence, beta hat iv would be z prime x inverse z prime y. What is z prime x? If you multiply the transpose of z with x, the first column of x is 1s. So, if you multiply this, you have 1 into 1 etc. n times. So, you get n. First column of z is 1. Now, this becomes the row z prime, and the first column of second column of x is x1, x2, xn. So, if you multiply this with 1 and then sum up, you get n times x bar. The second row of z is either 1 or minus 1. How many of them? Half of them are plus 1, half of them are minus 1, and the first column of x is 1s. So, if you multiply this, half of the products would be plus 1, half of the products would be minus 1, and they would be summing up to 0. And if you multiply the second row of z prime with x, then the 1s would pick up the larger values, the minus 1s would pick up the smaller values. So, what it would do is that you get the two means. There would be n by 2 plus 1 values and n by 2 minus 1 values, and the larger values, let us call this x 2 bar. So, this is the mean of the x's which are greater than the median, and the mean of the x's which are smaller than the median, let us call this x 1 bar. So, this becomes n by 2 times x 2 bar minus n by 2 times x 1 bar. Similarly, when you multiply z prime with y, the first term would come out to be n y bar, this is the first element, and the second element would be n by 2 y 2 bar minus y 1 bar. Mind you, these are not the larger values of y's and the smaller values of y, it is just it corresponds to the values y 2 bar are the ones which corresponds to the larger values of x, and the values y in y 1 bar are the values which corresponds to the smaller values of x. We do not segregate by y, mind you, we are segregating by x, and naturally these are pairs. So, automatically y gets segregated. Y may not have in fact, if it is inversely related, then it can be that the larger y's are in y 1 and the smaller y's are in y 2. And then if you do the inverse, you know that you are looking at a 2 by 2 matrix, you take the inverse, and after some calculations you get beta 1 hat as y 2 bar minus y 1 bar by x 2 bar minus x 1 bar, and y beta naught hat would be y bar minus beta 1 hat x bar. So, this would be the Wald's solution to the instrumental variable technique for errors in variables. Now, after Wald, Bartlett thought of a different method. He said that to get better results, we should be removing the middle observation. So, he took Zi as 1 for the larger values, that is the largest n by 3 values, minus 1 for the smallest n by 3 values, and 0 for the intermediate n by 3 value. It need not be exactly n by 3 because n may not be a multiple of 3. So, what you should do basically is, you have the two extreme sets should be equal. So, if you have 20 observations, maybe you take 7 as the largest values, 7 of the largest values in the first group, 7 of the smallest in the second group, and the remaining 6 in the middle group. So, the middle group values you are putting a 0 against it. So, when you take the product, all this would vanish. And by the same sort of algebra as we did before, beta 1 hat to turn out to be y 3 bar minus y 1 bar by x 3 bar minus x 1 bar. What is y 3 bar? It is the average of the larger values of x. It is the average of the y values corresponding to the larger values of x, and the average of the x's would be x 3 bar for these larger values. The average of the x's for the smaller values would be x 1 bar, and the corresponding average of the y's would be y 1 bar. So, we get beta 1 hat. Now, there is a third method which is referred to as Durbin's method. Durbin suggested that you take as an instrument Zi which is rank of xi. So, instead of Wald and Bartlett's method where they are taking just minus 1 for all the small values and plus 1 for the large values, Bartlett says that you just take the rank, and therefore his Z is, the first column is going to be 1 and the second column would be the ranks of the xi. And again, if you look at the normal equations, the first element is going to be n as before, that is the 1 1 cell. The 1 2 cell is going to be n x bar. The 2 1 cell, basically the second row of z prime into x, second row of z prime is the ranks. So, it has to be 1 to n, and x first column is 1. So, sum of the first n natural numbers, it will be n into n plus 1 by 2. And the last element, the 2 to 8th element, is you have the ranks and the xi's corresponding to each other. So, it will be sum of xi into rank of xi. This matrix 2 by 2 matrix into beta naught beta 1, this vector is equal to, similarly for the y's, n y bar, and the second element is summation of yi or rank of xi. And then if you do some algebra here, it turns out that beta 1 hat is summation yi rank of xi minus y bar n into n plus 1 by 2 by summation of xi into rank of xi minus x bar into n into n plus 1 by 2. And beta naught hat as usual would be y bar minus beta 1 hat x bar. So, this is Durbin's method, and generally Durbin's method is considered a better method because we are not taking just the same value for all x's which are small and all x's which are large. We are taking ranks which are slightly different. So, it basically evens things out much better. But more importantly, if you have several variables, we are looking at only one explanatory variables. If you have several variables, then if you are using the Wahl's method or the Bartlett's method, you will have to make the divisions in terms of one of these variables. That is, you have to choose, if there are p x's, you will have to choose one of the x's and find its median and then subdivide the two groups according to whether they are greater than this median or less than this median, and the other variables do not come into play. But if you are looking at the Bartlett's or the Durbin's method in this case, for each of the variables we can get the rank of the variable and insert the ranks. So, the Durbin's method basically can be very easily extended to a p variable case instead of the single explanatory variable case that we are looking at, and we can construct the z much more readily, much more logically for the Durbin's method than for the other methods. Now, let us look at an example. In the example, we have a response y and an explanatory variable x which are both measured with error, and then there are 20 observations. What we have shown here is both the maximum likelihood method and the instrumental variable method, and you will see that they give you quite different results. In the maximum likelihood method, we start by computing the x bar, the y bars, sxx, syy and the sxy. These are the values that come out. We will be using the fourth case as we have discussed in the last module, that will be using. In this case, we will take lambda equal to 1, because if you look at the observations, they are very close to each other. So, we will be assuming that the variances would also be, the error variances would also be very close to each other, and therefore, the ratio of the error variance is taken to be equal to 1. And if we do that, then we know that we get a quadratic in beta 1, and solving that quadratic, we find that beta 1 hat turns out to be, gives you two solutions, minus 0.84 and 1.19. But since sxy is positive, it is 8.07, we discard the minus solution, that is minus 0.84, and take the solution 1.19. We have got all the other parameters. Once we get 1.19, of course, mu hat is x bar, which is 19.24, beta naught hat is now y bar minus 1.19 into x bar, which is minus 2.78, sigma x star hat square is 6.78, and we can calculate sigma w hat square is 4.22. And if you go back to equation 4, you would get sigma b square, you can calculate it, and it comes out to be 4.22. But you should not have done that, because we know that sigma w square is equal to sigma b square, because our lambda is equal to 1. But even numerically, we can see that it verifies the fact that lambda is equal to 1. If you have lambda 1, then our calculations are right, and sigma w square estimate comes out to be the sigma v square estimate as well. Instead, if we use Wahl's method, we have, dividing this into two groups, 10 observations each depending on the median. We have y2 bar is equal to 21.61, y1 bar is equal to 18.63, which are the y's for the two groups, the larger and the smaller x groups, and the smaller x values are, mean of this is 16.53, and for the larger one is 21.94. And if we look at beta 1 hat, it comes out to be 0.55. Similarly, we can calculate beta naught hat from this. Bartlett's method is similar, and in this case beta 1 hat comes out to be 0.72. If we use the Durbin's method, beta 1 hat turns out to be 0.70. So, unlike what we got for the maximum likelihood estimator, in all these cases the beta hat comes out to be less than 1. So, there would be differences, but there is very little as far as the choice is concerned. One thing that we should keep in mind is that when we do the maximum likelihood method, once we get the maximum likelihood method, we can use all the properties that maximum likelihood estimators generally have. So, all the very nice properties, but serious assumption regarding a restriction. So, we are taking lambda equal to 1 in this case. Is that plausible? The plausibility condition, plausibility of the restriction would come in. We are doing nothing as such for the instrumental variable technique, but the question would be, is the instrument good enough? Are we taking a good instrument? Of course, the Durbin's method is the best because xi's are being related to their ranks and hence would be much more closely related to. So, zi and xi's would be highly related, larger xi, the larger would be the rank, etc. But both has some assumptions, both has some implicit mechanism that we need to look at, and it is very difficult actually to say which one is better than the other. It is always the experimenter and his concept that would come into play when we look at this. But the important thing is that when you have errors in variables model or when you have proxy variables, we cannot go for the ordinary least squares. We either need to look at the maximum likelihood method or the instrumental variable technique. In today's module, we had been discussing the instrumental variable technique of estimating the parameters of a error contaminated model or a proxy variable model. We have seen that we need to judiciously choose an instrumental variable which should be highly correlated to the original variable, but should be uncorrelated to the errors. And if we can do that, we can get reasonable estimates which should be consistent for the parameters that we are looking at. So, what we had been doing in the last 2 or 3 modules is that we had been looking at unobservable variables. We saw that using the least square does not give us very good estimates, they lead to inconsistent estimators, and hence we need to take recourse to either the maximum likelihood technique or the instrumental variable technique to get over the inconsistency and get good estimators for the parameters.